Okay, so review of power functions. Now remember, power functions have the following form: x raised to the n power. Now there are a few scenarios to consider. What if n is negative? What if n is between 0 and 1? And what if n is greater than 1? Now, we'll start on the far right because I think that one's a little bit easier to kind of figure out. A good example on the far right could be y equals x squared. So in this case, n equals 2. Of course, 2 is bigger than 1. Well, we should know the graph looks like this. What if you did y equals x cubed? That would look like this. And if you do anything where n is bigger than 1, like x is raised to the 1.1 power, x is raised to the 4th power, whatever, we're always going to expect the first quadrant to have this kind of shape. So it definitely will be increasing. And also the slopes of our tangent lines, which is kind of important. That's a kind of a main topic in AB Calculus AB for the first semester. The slope of the tangent lines keep increasing. For example, if I drew that tangent line that has a positive slope, would you say this one has a more steep slope?
Yeah.
Totally, right? Absolutely. So that's what we kind of anticipate, because we're going to be working through these functions often in the first semester. Okay, so that's what we expect for a power function when n is bigger than 1. Now, what if it's between 0 and 1? So let me do a different color here. Let's say n is 1/2. So a good example would be y equals x to the 1/2 power, which hopefully recognizes the square root of x. Well, we know that graph looks like this. Even if you did like the cube root of x, which is that, x to 1/3, the graph still looks pretty much the same. It actually looks like this. Because you could plug in negative numbers. You couldn't do negative numbers for root x, but you could do negative numbers for cube root of x. But the bottom line is that the first quadrant will always look like this. Now, in this case, it is also an increasing function. But the slopes of tangent lines decrease.
Okay.
So you see how like the slope gets a little bit less steep. It's still going to be positive, so that indicates that you have an increasing function. But yeah, it just kind of starts declining. So it's kind of a slower increase if you want to think of it that way. Okay. And then lastly, what if your n is less than 0? So let's erase this here because I need some space. What would you like to say n is?
Maybe like -1.
Great, perfect. I love it. -1. So y equals 1/x. So what that would look would be like that.
Okay.
Right? Or what if like n were -2? 1/x squared. Now, because you're squaring x, y is always going to be positive. And of course, the domain of won't include 0. So we expect something like this here. So this case would be a decreasing function. But believe it or not, the slopes of our tangent lines will increase because what happens it's very negative, but gets less negative as time passes. Actually, it's closer to being to 0, but not exactly 0. So that's what we kind of anticipate. Now, things do get a little bit weird when you do go to the left of the y-axis, when you look at like the second or third quadrants. And a lot of it kind of depends on whether you have an even exponent or stuff like that. So there's some wonky things that could happen, but we'll worry about that in a little bit. So those are the basics of power functions. If we go back to the summer assignment really quickly, we could probably gather, well, actually, all these are exponential functions, never mind. So we'll come back to that in a little bit, but I do want to have this discussion about power functions. So to get the rest of the graph, we need to consider, right, does a graph exist for x is less than 0? Like, obviously you can't square root negative numbers. If it does, then we need to establish whether it's an even or odd function. And so to do that, I'm not sure if you've had that discussion. Have you had that discussion on even or odd functions?
No.
Okay, so it's really a really simple concept. If you have this, we call that an even function. If you have this, we call that an odd function. So, for example, y equals x squared. And y equals x cubed. That's kind of a great way to contrast. I'll make a little table off to the side here for both. Obviously, when x is 2, y is 4. When x is negative 2, y is still 4. So what this tells me is that f of 2 equals f of negative 2. That totally follows that rule right there. And also we notice that it's symmetric. My screen's cracked here. Symmetric about the y-axis. So the y-axis kind of cuts that in half, which would make sense because you want the left side to be a mirror image of the right side. It also happens that the exponent is even. Not sure if the name comes from that, but we don't really focus too much on that because there are other functions like trigonometric functions that follow this kind of guideline. So I don't really try to put too much emphasis on that. But there's an even exponent there, which kind of makes sense. Now here, if you plug in 2, what do you get for x cubed?
6, right? 6.
No, 2 times 2 times 2.
8, sorry.
How about negative 2?
It would be negative 8.
Exactly. So in this case, f of 2, which is 8, is going to equal negative of f of negative 2. Or you could say, just to be consistent the way I wrote it on the top right, f of negative 2 equals negative f of 2. Because f of negative 2 is negative 8, f of 2 is 8, but putting a negative in front of f of 2 makes it negative 8. So we call that an odd function. And that's going to be symmetric about the origin. Meaning that if I rotated this graph here 180 degrees, it would get back to the same configuration. So those are other things that we need to consider as well when you want the complete graph, in addition to seeing if the domain would exist when x is less than 0. Because if the domain doesn't exist, and you know the domain wouldn't exist if you're doing any even rooting, like y equals root x, or y equals x to the 3/4, because that's the 4th root of x cubed. Like, that's not okay. Your domain would not be existent for less than 0 for that. So y equals x to the 2/3. Why we're interested in knowing how to graph that? Because we are going to be doing derivatives of those kind of functions. And in order to do derivatives are basically slopes of tangent lines. We'll just have that discussion down the road. But in order to understand that, you have to understand how it looks. So, that's just for good calculus teaching. We have to understand how our graphs look. So before we get too carried away by doing calculus principles of the stuff, we want to make sure we understand the graphs. So now, what is my n here? It's 2/3. Of the three conditions we talked about, is it less than 0? Is it between 0 and 1? Or is it greater than 1?
Between 0 and 1.
Yes, good. So it's going to be this kind of scenario. So at the very least, we know that. So that's what we'll do. So the curvature also kind of matters too, and that will be more obvious once we get to you know, the second or third unit of calculus. Now, does it exist? So remember, that's the cube root of x squared. Well, yeah, of course. You could plug in negative numbers, sure. So we are going to have some stuff to the left. So then, is it an even or odd function? So what you could do is replace x with negative x.
Okay.
What happens when you square negative x?
It becomes positive.
Still, yeah, back to x squared. So we're back to what we had before. So when that happens, that's an even function. Or if you so desire, some people just like to plug in a number, like plug in 2. You get the cube root of 4. Plug in negative 2, you still get the cube root of 4. So the answer is an even function. So it's going to be symmetric about the y-axis. That's how the graph looks.
Okay.
And actually, if we were to venture to Desmos, I know it's really messy, but y equals x raised to the 2/3. Yeah, you see, we get that. So sometimes those are daunting, the graph in pre-calculus or algebra 2, but you know, but I think now that we have seen this stuff for a while and we have a, you know, just stronger critical thinking skills, we feel more comfortable doing these graphs. And this is going to be important because we have to calculus principles with these types of functions. We have to understand how they look. Okay, so now let's take a look at maybe some of the examples here, and then we'll go back to the summer assignment. So there are a total of 8 problems. Let me do maybe 2, 6, 7. So I'm going to kind of do like one of each case because they look kind of weird, right?
Yeah.
So let's identify n in each of these cases here. So of course, n's between 0 and 1 for number 2. N's bigger than 1 for number 6. And n is less than 0 for number 7. Okay, so I enabled screen sharing. Go ahead and draw for me the first quadrant for each of those 3 graphs. So
How do you draw on here?
If you move your mouse all the way up, and then you should see a drop-down menu. You should see annotate.
I don't see it.
Sometimes it could be a little pesky. Yeah, just keep moving your mouse all the way to the top of the window. It should pop up.
Oh yeah, there you
go. Okay.
Okay. So for this one, so that. Like that.
Great, perfect. Now, remember, this is the 5th root of x to the 4 power. If I were plugging like -1, would that be okay?
Yeah, it would stay
yeah,
positive.
Yeah. So domain includes x is less than 0. So then what we do is we replace x with negative x and see what happens. So taking the fourth root keeps it positive. So we get back to the same thing.
Okay.
So actually, that's our graph. It's the same thing as y equals x to the 2/3. I mean, not technically the same graph, but it's close enough.
Yeah.
So this tells me something, that if my numerator is even, and my denominator is odd for the exponent, I'm going to get that kind of graph.
Oh, okay.
Now, if it were the other way around, which we have in number 6, let's see what happens there. Of course, the first quadrant looks like that. So this is going to be y equals the fourth root of x to the 5th power. Now, will the domain exist when x is less than 0? So if I were to plug like -1 in, would that be a problem?
It would be negative, so yeah.
Yeah, that'd be a problem. So that's it, you're done.
Okay.
You're done. You know, so you don't do anything to the left of the y-axis. Just leave it like that.
Oh, okay.
Because you're even rooting. That's the other thing too. Then for number 7, that's like saying y equals 1 over the cube root of x squared. So can x be less than 0? Could we play like -1? Would that be okay?
Yeah.
Yes. So domain includes it. Sorry, messy handwriting. Domain includes that. Then, what if I plug like negative x? That's 1 over the cube root of x squared. So it stays the same. So it means that the other side just looks like this.
Okay.
Now, what if I just did a little slight twist here? What if I did y equals negative x equals negative 5/3? So now I have 1 over the cube root of x to the 5th power. Now, if I were to replace x with negative x, what happens when you raise negative x to the 5th power? Does that stay positive or it becomes negative?
Negative.
Exactly right. So now that's an odd function because the sign changed. Everything else looks the same. So I would then have to do this.
Okay.
So in this case, it's interesting that when the denominator stays odd, but then the numerator is odd, that we see something in the 3rd quadrant. So we have to kind of take these on a case-by-case basis.
Okay.
Yeah, so that kind of exemplifies how we handle our power functions.